Well, guys, this is it. The day that I told you was coming quickly, and oh my gosh, it's here. Sneak this in here. So, guys, let me just be really upfront with you right from the start. This is a hard day for me to know how to handle. Not because it's the last day of material, but because they took these equations off the AP equation sheet. Yeah. So, no, it is. I mean, if you were to ask anybody in general physical chemistry, and specifically electrochemistry, what is the most important guiding principles that you can teach high school students or early college students, they would say it's all encapsulated in the Nernst equation. Because the Nernst equation and one of its derivatives, which you'll see at the end of the day today, guys, links so many different ideas together. Because we're going to link voltage, we're going to link equilibrium, we are going to link everything that we know about concentration changes, and we're going to link it all to the real world experience that batteries die. And it all gets told through this equation, and the head shed that runs the AP chemistry program said, guess what? Let's get rid of it. Good heavens. So what are we going to do? Well, guys, we are going to go ahead and expose you to this content because the concepts are great. And understand that you don't get to totally wash your hands of this because batteries die. And as they die, they reach equilibrium, as we talked about a minute ago. And they still expect you to understand equilibrium. Apparently, they just don't expect you to do the math. So, guys, what you're going to find is this. A lot of these slides are conversational. Be judicious in the notes that you take. I am going to share with you the equations that come from these concepts. But guys, the way this is going to go is I'm going to set the stage for the Nernst equation, and then I'm going to give it to you, and then we'll talk about the math, and then we'll talk about the practical conceptual idea behind it. And then, guys, we'll take the Nernst equation, we'll rejigger it, we'll talk about equilibrium, and that's not only the day and not only the unit, but also the year. If you only knew the struggles that I have with our school song, because they force us to sing it at faculty meetings.
No, like in the mornings when you guys are like in a little.
Yeah. If you want to see a little slice of funny, the first Wednesday of every month, plan to get to school at 7:25 and sneak by the little theater and come and watch the faculty sing the school song, keeping a careful eye on Mr. Reed and Mr. Steele, who I think you all would agree are probably two of those little like vessels of school spirit, right? I mean, these are men that have dedicated their lives to this school, not only as teachers, but as coaches, as mentors of students. I mean, I've aspired for a long, long time to be, frankly, like Mr. Steele. He's an amazing man, beyond who he is as a coach and a teacher. Come watch him sing the fight song. It's a little bit of okay. You'll love it. So, yeah. We only have two more, April and May, and then you missed your window. But first Wednesday, 7:25. We may not. Oh, maybe we only have one left. Yeah. Have you guys ever heard the guiding principle in business that says never do in a meeting what can be effectively covered in an email? I'll leave it at that. Okay. Okay, so guys, here we go. All right, let's talk batteries. So guys, here's the deal. A couple times ago in class, prior to our conversation about weak and strong oxidizing and reducing agents, we talked about batteries, and we drew the schematic of the battery up on the wall, and we labeled it, and we talked about its pieces and parts. And we even calculated its voltage. And guys, as we calculated its voltage, we did the cathode minus anode math, right? And for the zinc copper battery, we said 1.10 volts. And we came up with this number. But guys, we now need to talk about that number. When does that battery make 1.10 volts? Initially, so long as initial is what? It's what the little circle means. Standard conditions, which is it 25 Celsius? I think it's 25 Celsius, but guys, the important bit here, 1 molar solution concentrations. And guys, what you're going to find out and what you know practically is that batteries die. And again, it's amazing what they can do where the death of a battery is not linear. It's sort of the cliff that we talked about, but I would love to know how they do that. It's magic. But guys, the batteries that we build, these simple zinc copper batteries and things like this, they taper linearly. From the very minute you mix them together, they die. And we can actually describe that death. And we can describe it mathematically, because as batteries die, what's changing about the cell? Can we talk about that quickly? Yeah, but that's not it. That's not the only thing. So let's do this. So guys, imagine our battery, and you may want to write this down. And let's keep this right, because you guys are creatures of habit. Which was it? We're doing the zinc copper battery. What did we put on the left? The zinc. Okay, zinc was oxidized, right? So this was our oxidation. This was our reduction. This was our zinc. If you want to, and guys, really, I know you can go back in your notes and look at this again, but there may be value in scratching this together, because doing this repetitiously, you're going to find is important. So guys, if this is our battery, and we remember that this is zinc solution, and this is copper solution, disregarding our spectator anion. And guys, if you don't believe you've learned anything this year, think about the fact that you just heard the word spectator anion and you all knew what that meant. September, you had no clue. September, you learned about spectators and net ion, and now so much of this stuff is just becoming inherent in your understanding. Anyway, so oxidation means losing of electrons, right? So which direction do we draw our arrow? Is solid zinc going into solution or ion being deposited as solid? Left to right or right to left? Left to right. Oxidation is the loss of electrons. These guys are going into solution. And then, guys, we could even then say that that makes this the negative side, because oxidation at the anode releases electrons. They travel through the external circuit. And then this, of course, is where we have the opposite and yet complementary process, which is reduction, where the ion in solution is being deposited as a solid. So guys, Caleb said something important a second ago, that as this battery moves from life to death, the solution concentrations are changing. And I think you know this, but let's be clear, because they both aren't changing the same. What is happening to this zinc solution? More or less concentrated? More, right? And we mentioned that before, but it's worth mentioning again. Guys, in the oxidation compartment, this concentration of the solution is going up. So what's happening in the reduction compartment? The solution concentration is going the opposite, down, right? But then, guys, remember, you also have to understand this through the lens of the electrodes. What is happening to the mass of the zinc electrode at the anode? It's becoming less massive. Where are the zinc atoms going? Into solution as ions. And what's happening to the mass of the copper electrode? Of course, it's going up. Where's the copper coming from? It's depositing out of solution as the ions are reduced to solid. Is that all ringing true with you? Is that okay? So guys, how then does this work? well, what is going on in this battery that would drive it towards death? And when we talk about this, we don't think about the mass of the electrodes, we think about the concentration of the solutions. Because initially, when this has got 1.10 volts, what are their molarities? 1. What happens to the molarity of the zinc? It ends up higher than 1. What happens to the molarity of the copper? It ends up less than 1. And guys, if you watch my hands, here's what happens. And I think this is part of what made it hard for me to answer the question that Everett brought into in homework, was I was trying to draw on too much chemistry. Because here's what happens. When a battery starts, they're both at 1 molar, right? And I'll try to do this so it lines up with what's on the board. So oxidation's on the left. Okay, so guys, what happens then is the concentration of the oxidation cell goes up, the concentration of the reduction cell goes down, and we end up with what's called the concentration gradient. Can you see that? Okay, what happens then is when that concentration gradient is offset by a voltage gradient, the battery dies. Because we've also got a voltage gradient. Remember, it's the difference between the oxidation and the reduction. It's voltage. And so when that concentration gradient is offset by the voltage gradient, the battery's done. So we can describe this process mathematically as these batteries move towards death. And you can think about it this way. Eventually their concentrations get so out of whack that the voltage isn't enough to push them against the concentration gradient. Do you see how that works? So the idea literally being, guys, that the concentrations go like this, and eventually the voltage is not enough to keep the battery going against that concentration difference. Yeah. Well, so think about the things that we know. Well, let me back up. Yes. And you found that out in lab, that you created that, and actually you and I talked about it because it was that one that you weren't sure about the volumes on. That's called the concentration cell. You can actually create a battery that runs even if the substances are the same, just by having different concentrations. So say, for example, these were both copper. Okay, so if we were to change this to copper, we could actually still make that a battery even though there isn't an oxidation reduction potential difference. Let me draw this for you. So it would look like this. So we could do this. We could create, and I'm just going to really scratch this together. Say that this is copper, and this is copper, but this was, let's say, 10 molar copper. Come on. This is 10 molar, and this is 1 molar copper solution. That's a battery. Even though it's the same substances, this will function as a battery. And here's how. This is a higher concentration, and so just the laws of entropy would tell us, well, the collision theory of reaction would say that some of this is going to deposit because there's so much more of it. Some of this will go into solution in order to offset the charge. And as this is oxidized, we would get a flow of electrons that goes this way and it's just across a concentration gradient. They're not very effective batteries, but they work. Exactly, precisely. But with that said, the thought then, because you ask about this idea of competing gradients, and the idea is this, that one of the things that drives reactions is voltage. Another thing that drives reactions is movement towards equilibrium. And in batteries, they're fighting against each other. And so and so the voltage pushes in one direction, the concentration gradient pushes in the other, and eventually they cancel each other out. So, yeah. Okay, so guys, with that said, here then, let me give you the notes that support what we just talked about, and then we'll look at the math. So it goes like this, and again, guys, please, you don't need to write all this down. It's just a summary of what we talked about. So to this point, as we've just studied batteries, we've talked about, or we've assumed, 3 things are true. First of all, voltaic cells are spontaneous. How do we know? Because we pick the oxidation and reductions, the anode and the cathode, such that they have positive voltages. But we've also only studied these at standard conditions, which is an atmosphere pressure 25 Celsius and 1 molar solutions. Well, guys, this works, but this really doesn't tell us about what batteries are doing for real. So, as we now understand, when batteries do their battery thing, the concentration changes. But guys, notice the answer to this question is not concentration goes up or concentration goes down. What is the answer to this question? What happens to concentration as the battery goes? The concentration at the anode goes up, and the concentration at the cathode goes down. So it's not one answer, it's both answers. And if you need to write that down, it's worth defining for sure. Guys, the solution concentration at the anode goes up, and the solution concentration at the cathode goes down. So anode up. Ooh, still consonants and vowels. Anode up, cathode down. As if it all made sense. Yeah. Yeah. Yeah, and so it's similarly, it's that down. Yeah, absolutely. So guys, what then eventually happens? Well, eventually these batteries reach equilibrium as reactants become products, and eventually these cells die. And when they die, the electromotive force becomes zero, and the battery is dead. So the question then is, how do we understand this process mathematically of batteries dying? And the answer is the Nernst equation. So what I'm going to do is I'm going to give you the Nernst equation, and then we'll define the variables, and then we'll apply the Nernst equation to our good friend, the copper zinc battery. And then we'll talk about how we can adjust the voltage of this battery by changing concentrations. We already sort of talked about it given Carson's thought, but we'll play with it some more. Yeah.
So like when the battery dies, if you were to decrease their concentration,
You bring it back to life. Yeah, yeah. Understanding though that changes in voltage brought about by concentration change are not significant compared to the changes in voltage brought about by different components that have wider ranges in their oxidation potentials, reduction potentials. Okay. All right, so guys, with that said, here it is. The Nernst equation. So what does the Nernst equation let us do? And the answer is it allows us to figure out voltages at non-standard conditions. Not relative to temperature or pressure, but relative to molarity. So guys, the Nernst equation allows us to track voltage as the concentration changes bring a battery towards failure, towards death. You'll notice that there's our good friend Q, right? Which we just talked about. Q is Kc at non-equilibrium conditions. So guys, let me define variables. I'll bet you can figure these out though. So what is E? E cell. It's the voltage of the battery at any given moment in time. What is E naught cell? That's the standard voltage. That's the one that you learned to calculate 2 days ago. Then guys, N is the number of moles of electrons. We've talked about that previously. And then Q is the reaction quotient, which you remember is just Kc at non-equilibrium conditions. And we used that previously to figure out which direction reactions move at any given set of concentrations. Yeah. No, it's the concentrations of the ions in both cells. Zinc and copper. Uh-huh. Yeah. Yeah, and what I'd like to do is I'd like to talk about that generically now and then specifically on the next slide, because we're going to look at that. Gil?
Hey, sorry to interrupt you.
No.
The day you picked is the day of the Spirit Bowl
Yeah,
for your team.
that was on purpose.
That's not gonna work.
We figured it was a day that was going to be thumped, and it was actually a day when it worked into what we were doing in class.
The subs and then they're gonna require or ask that we go to the Spirit Bowl.
But that's okay, right? Because isn't it after second? Because we thought we'd do Spirit Bowl and then go to third and fourth and let the subs just do our third and fourth periods after Spirit Bowl. Is that okay?
Guys, see the schedules.
Okay, because but seriously, the reason we did it was looking at our lab schedule and looking at our test prep schedule for AP. It was all a period that, like, these guys are going to be doing their first sample test. I know, I don't either. Yeah, no, I know. Understand, it was for me, it wasn't for them. But yeah, no, we just figured.
Check with Mike.
Is that okay? Okay, yeah, okay.
So, okay.
Okay. So guys, let's do this, and I think you're going to want to do this with me, but let's do this before we start looking at this practically. Guys, remind yourselves about Q. Q is the same ratio that's Kc, right? So what is it? Well, it's products divided by reactants. So let's no, that was my fault. I'll own that one. So guys, Q is Kc at non-equilibrium conditions. So this is products divided by reactants. So guys, given that, let's talk about the significance of this subtraction sign. So how does this work? Well, guys, let's blend the math and the chemistry together and understand how the math describes the chemistry. So guys, first of all, this is a known quantity. It's sort of like a constant. It's a constant. What do we know about N? It's the number of electrons, right? So what does this always have to be? Positive, right? We'll always have a positive number of electrons. Now, guys, let's do this. We know that Q is the ratio of products divided by reactants. And guys, the thought here then becomes this. What happens as a reaction goes on? So as a reaction does its reaction thing, what happens to the concentration of products? It goes up, right? What happens to the concentration of reactants? It goes down. So now, guys, let's have sort of a little logarithm conversation. So the idea is this. As the numerator goes up and as the denominator goes down, what happens to the value of this fraction? It increases, right? So what then is the value? What is the value of the log of a number bigger than 1? And do you understand why that has to be bigger than 1? Because this is going up and this is going down. Big divided by little will give us numbers bigger than 1. So what is the log of a number bigger than 1? Positive. Guys, when is a logarithm negative? When it's smaller than 1. That's an important idea. We'll come back to it in a minute. So the idea is this. As the reaction goes on, this number gets bigger, this number gets smaller. The log of that ratio will then be a positive number because it's bigger than 1. So notice what we've got. We've got a positive number here. We've got a positive number here. We've got a positive number here. So this entire expression then will be positive. And as the reaction goes on, what will then happen to the magnitude of that positive number? It'll get bigger and bigger and bigger and bigger and bigger, right? Because this is getting bigger and this is getting smaller. So as the reaction goes, this gets bigger and bigger and bigger and bigger and bigger. And eventually, this gets so big, do you see it? That when you subtract it from this, it ends up being 0 and the battery's done. Do you see it? So guys, what is this value? This is the battery at standard initial conditions. But as the battery does its battery thing, this gets bigger and this gets smaller, making the magnitude of this more and more positive, but we subtract it, and as we subtract it, as soon as this becomes the same size as this, the battery's dead. So guys, do you see how this equation describes these competing gradients? This is the oxidation reduction gradient. This is the concentration gradient. And as soon as that concentration gradient, and I like now, Carson, even more the way you said this, that the concentration gradient creates sort of like its own voltage, and we can even describe it in volts because we're subtracting it. Guys, as this goes on, eventually the concentration gradient offsets the voltage gradient and the battery is dead. Do you see how the math describes the reality? Is that okay? Okay. So guys, let's then talk about a real life example. Don't write down the questions, but do write down your answers. So here's our good friend zinc copper, right? So guys, and I would encourage you to write down the answers to these as we go. What's the Kc expression for this? Write it down. For some of you, you're going to be surprised. This might be a time when it'll be nice to have the extra wide screen because maybe I can leverage that space. So guys, what does Kc look like? Well, Kc right? Yeah? Yeah, because guys, the zinc and the copper are solids. This is a heterogeneous equilibrium. They don't have concentrations. So the Kc expression is simply the concentration of product zinc ion divided by the concentration of reactant copper ion. Hunter, go ahead. Yeah, they should be, and notice I wrote them correctly. I typed them wrong, but wrote them right. Yeah.
She is not being able to get full day subs for 4 out of the 6 that are
Okay, we need to switch days. Okay.
So decide today, and let me know.
Yeah. Yeah. No, it's totally fine. Yes, I'll need to get everybody in the same room.
You guys have to do the sage training today.
Exactly.
We're all going to be sitting together anyway.
Okay.
Does that
Okay.
sound good?
Yeah, for sure. Thanks, Gil. Okay, so guys, you good on this? Hey. Yes, this went longer than I thought. Maybe. Yeah, okay. If all I had to do was teach, my job would be so easy. Seriously, and it's really, they've done fascinating research on this about how little students know about what it means to be a teacher. It's crazy. What I do with you is about 20% of my job. It's ridiculous. So guys, Casey, you good on that? Okay. So guys, what about this then? How many electrons are being exchanged in this process? Can you see if just right out it's 2? Zinc goes from 0 to +2, copper goes from +2 to 0. It's 2 electrons. Then guys, what about this? The EMF, the voltage for this cell is 1.10 volts. But they won't give you that on the test. But how did we know it was 1.10 volts? Cathode minus anode, right? So how would, and again, let's review, how would we know which one is the cathode? Where would the cathode be on the chart? Higher or lower voltage? Higher voltage, because this is a reduction potential chart. And what happens at the cathode? Reduction. And so guys, the one with the higher voltage would be your cathode, and then you go cathode minus anode, and that gives you 1.10 volts. Again guys, this will not be given to you necessarily, but it's quickly calculated. Then this, come on, we know where that came from. So guys, given this information then, set up the Nernst equation. I'm going to just do it up above. Oh, okay. And of course, guys, you would need to write it all down, but I don't have room. I think that's right. And you understand that's 1.10. It just drug. Are we good? Yeah.
I have a question. So, isn't the end supposed to be the moles of electrons?
It is.
Just the number? So
Well, but understand they're interchangeable because particle relationships in balanced equations can be represented as individual particles, an atom of this plus an atom of that, but it can also be a mole of this plus a mole of that. So it can also be understood to be in moles. And when we deal with concentrations, these are molarities, moles divided by liters, so the units are understood to be moles throughout. 2 moles of electrons. Yep. Okay. Are you okay with that? Okay. So then, guys, this is where I really think they're going to go with this on the AP test. What could you do to make the voltage go up? What could you do to this cell to make the voltage go up? Well, let's talk about it. In order to make the voltage go up, the only thing that we can change is this, right? So what change to this relationship would make the voltage go up? Well, what do we want to do to this? We want to make it smaller, right? So how do we make this smaller? By adding copper ion, or technically you could precipitate zinc. But guys, here's the thing. You've got to be really careful. Did you notice how I explained that to you by going right to the Nernst equation? But guys, let's understand this without going to the Nernst equation. Let's look at the balanced equation in blue. If you didn't even have the Nernst equation and you just said, how do we make this reaction go better? What would you say? Add reactant, right? If you want a reaction to do more reacting, what you want to do is add reactant. And what's our reactant? Copper ion. So guys, adding copper ion shifts the equilibrium to the right, increasing the volt, driving the equilibrium to the right, increasing voltage. We see that here chemically, we see it here mathematically. But then guys, what if we asked the other question and said, what if we wanted to decrease the voltage? Well, then we would do the opposite. We could add zinc ion, again making the value of the fraction greater, but chemically we can see that if we add product, we are making the reaction less favorable, decreasing the voltage. Is that okay? So now guys, and we're not going to do the math, but let's talk about what it might look like. What if we wanted to answer this? What is the voltage of the cell if copper ion is 5 molar and zinc ion is 0.05 molar? Even without doing the math, what if we ask this question? Will the voltage of the battery be above or below 1.10 volts? I don't know the answer. You're saying above? Let's think through it. So which one are we making bigger? Copper? So copper is big, zinc is small. When we divide, that makes the value of this smaller. So we're subtracting a smaller number, so the voltage would go up. We may even be adding, we're probably adding a number. So the voltage goes up. Or we could look at it like this. We're increasing the concentration of this, decreasing the concentration of that, driving the reaction to the right. So in either case, we understand voltage goes up. Do you buy it? Okay. So now, guys, this, wrapping up the day. So, guys, not only does the Nernst equation allow us to study redox reactions as they're moving towards equilibrium, it also, because it's a window into equilibrium, allows us to relate Kc with voltage. And it goes like this. It's interesting. Guys, remember reaction quotients. What is the relationship between Q and Kc when a reaction is at equilibrium? They're the same, right? Q is Kc at non-equilibrium conditions, so if it's at equilibrium, Q is Kc. But what about this? What is the voltage of a battery at equilibrium? 0. It's dead, right? So guys, look at what we can do. Take the Nernst equation and solve it for these two realities. This is what the Nernst equation, don't write it down yet, but guys, this is what the Nernst equation looks like when the battery's dead. Where is the fact that the battery's dead? 0 voltage. Where is the fact that at equilibrium Q is Kc? Well, we just replaced it. But now, guys, watch what happens. We can rejigger this equation and we can solve it for K. And when we do, we get this. Yep, this one you need to know, although it's no longer on the AP sheet. But guys, fundamentally what this tells you is this. If you know the voltage of a battery, you can figure out its K value. Or if you know its K value, you can figure out its voltage. Which maybe you can now understand how that became distracting for me as we were trying to answer the question in homework earlier, because we're talking about a different set of realities. Yeah. Well, no. So, sorry. Well, so if we know K, we can figure out the voltage of the battery at standard conditions. Yeah. What do you think, y'all? You good? Guess what? This is your last homework assignment of the year. We will grade this on Wednesday. We will then spend the remainder of the day on Wednesday talking about how we're going to wrap up this unit. And then, guys, we are going to look, as I mentioned before, into the face of our enemy. And we're going to start talking about what this AP test is going to look like.